Hello and welcome to the second video of Deep Learning from Scratch. In this video, I'm going to be talking about some terminology and then some matrix multiplication. So let's get started. So here you have a neuron with one output and two inputs. Let's denote the input as x1, x2, and its weights are w1, w2. So if you go x1 times w1 plus x2 times w2, you get the logit of the neuron, and that's z. Now z is just the net value, and so let's write z here, and to get from z to the output of the neuron, we have to pass z through the neuron's activation function. That is what defines what type of neuron it is. So the activation function is whatever it is. Let's just denote that as f, and z gets passed into this function. Now f outputs the output value, which is denoted by y. So let's move on. Let's talk about the whole network of these neurons. Let's say we have a 2 by 3 network of neurons. Each neuron is connected to each neuron in the next layer. So let's take the first neuron. That would be connected to this one and this one. And I forgot to say that these columns, they're called layers. And so let's just finish these connections. And let's give a name to each of these layers. The last layer is always the output layer, and the first layer is always the input layer. Any layer in between. Now, we only have one, but you can have as many as you like. They're all called hidden layers. Let's just call them let's not use I. Let's say O, M, and N. Actually, no. Let's use J, K, L. That's better. Let's give a name to each of these neurons. So the first neuron of the jth layer would be J1, J2, K1, K2, L1, L2. What would the weight between neuron J1 and K1 be? Well, that would be WJ1, K1. So it's the weight between J1 and K1. So that's pretty intuitive, and that would also work for any weight here. So let's do this one. This would be WK2, L1. The weight between this one and this one. So how do we write all these weights between J1, the layer J, and the layer K as a matrix? So let's try to write that. First of all, let's make this go away and write this here. So we can write it the first one would be WJ1K1, but we can write that as W11, the first number being and corresponding to the row number, and the second number is the column. So this one would be the same row but the second column, and so on. Now let's say we have an input value to this network, and that input is I1, I2. So you have I1 here, I2 here. This is how you denote it as a matrix. Now, what happens when we multiply these two matrices together? What happens is that we get the input to layer K1 and to layer K, and that would be K1, K2. And I'll show you why this is. It's because, first of all, how do you know you can multiply these two matrices together? Well, you look at the first matrix, you write down how many rows it has. Well, it has one row and it has two columns. So let's write that down. The second one has 2 rows, 2 columns. Now we look at the inside numbers that we just wrote. If they're the same, that means these two matrices can be multiplied by each other. Now, if you want to know what the shape of the resulting matrix is, that would be the outer numbers here. So if you put them together, you get a 1 and a 2. So it'll be 1 row and 2 columns. Here you have 1 row, 2 columns. So that makes sense. Let's try and actually multiply these two matrices together manually. So how would that look like? Well, first of all, you have to multiply two matrices together. You take a look at the first matrix, what the first number of the first row of that matrix is. That's I1. You times that by the first number of the first column of the second matrix. So that's I1 times W11, and you move along the first row of the first matrix, and you get I2 times W21, because you move along the column of the second one, of the second matrix. And you do this again for the second column of the second matrix, and you get I1 times W12 plus I2 times W22. And this is your resulting matrix. And it turns out that this looks really similar to the feed-forward algorithm and becomes the input to K1, to neuron K1, and this becomes the input to neuron K2. So, what if we have a different matrix here, and it's different in that the hidden layer has 3 neurons instead of 2. How would the matrix look like, the weight matrix between the jth layer and the kth layer? Well, let's take a look. The input matrix has 1 row and 2 columns. So we know that if we were to be able to multiply this by another matrix, it needs to have 2 rows to get the 2 inside numbers the same. So what would the matrix be? It will be W11, W12, W13, W. Okay, so it has 3 columns, and we know from looking at the outside numbers that the resulting matrix will have 1 row and 3 columns. So if we can observe that in the shape of the weight matrix, that the number of rows is actually equal to the number of neurons in the input layer, and the number of columns is equal to the number of neurons in the next layer, that is the hidden layer, the kth layer. So that is true when you're always trying to make matrices for the weights between two layers. That's that for this video, and in the next video we're going to download a matrix library called Eigen. It's a math library for linear algebra, and it's highly optimized, it's very fast, and it will do a lot of the math for us and make our lives a lot easier. So thanks for listening, and I'll see you in the next video.